Dear audience, welcome to the subject of signals and communication systems. I am Dr. Kalyan professor at KL University, Baurampet, Hyderabad. I welcome all the audience to this course on signals and communication systems. So in this introductory session, we are going to discuss about the signals, the systems, the basic introductions, and also the classification of the signals. So the learning outcomes of this session are you should be able to understand the concepts of the signals, you should be able to explore different types of signals, and you should be able to classify different types of signals. Now we are going to discuss what is a signal. A signal is a function of one or more variables such as time or space, and the signal it carries useful information. So the signal is a function of some multiple variables and it carries some useful information. For example, we take the speech signal. The speech signal is a function of time and it is carrying the useful information, which is the voice of the speaker or the communication. Now if we take some another example, for example, a biomedical signal, for example, ECG. Here the signal is showing the heart rate, and again this signal is also a function of time. Now another signal we can take is a image signal. The image signal, it is a function of the x-axis and the y-axis. So the image signal is actually a function of two independent variables, which is the x coordinate and the second one is the y coordinate. And video signal, it is a function of three independent variables. So it is consisting of the x coordinate, the y coordinate, and also the time, x, y, and t. So the video signal is actually having three independent variables. Now here we are showing the block diagram of the signals and systems. So we can see that the signal is described as x of t here, which is the input signal, and the system is being described as tau. Tau is actually whatever is the operations performed by the system, and the output signal is described as y of t. So if you see what is the basic block diagram of these signals and systems, we are describing a input signal which is x of t, and we are describing the system also, which is tau, which is a set of the operations, and we are also describing the output signal, which is y of t. So there is a input signal x of t, there is the output signal y of t, and in between the system is represented as tau. It is performing some operations on this input signal x of t and generating the output y of t. Now here we are seeing some example systems. So here the basic mobile phone or cell phone is being shown as a system. The cell phone which we carry in our pocket is nothing but a system. And the sound which is coming in and out in the shape of the speech, that is the signal. So in the cell phone system, whatever is the mobile phone or the cell phone, that is the system, and the sound which is coming in and going out, the speech signal, that is the signal. Now we are seeing another example of the signals in the communication system along with the various systems. So here we are seeing a microphone which is recording the signal of the speech. So the input signal is the audio signal or the speech signal, and it is being recorded by a system which is a microphone. And then in order to transmit over long distance, this audio signal must be converted to radio frequency signal, which is also called modulated signal, and that is being done by a mixer. Again, this mixer is a system. Now finally, this modulated signal is being amplified by using amplifier, which is another system. And this amplified RF signal or radio frequency signal is then given to the antenna, which is again another system. So we can see in basic transmission of the signals in communication system, we'll have multiple systems and multiple signals. Now we are going to study a very important topic here, which is classification of the signals. So we are going to start with the basic classification, which is continuous time signal, which is here x of t, versus the discrete time signals, which is here on the other side, which is x of n. Now the continuous time signals, they are the variables of the continuous time, where t is a continuous time variable. It can take integer values and fractional values. And the discrete time signal, which is also called a discrete time sequence, it is having a discrete time as the independent variable. And this discrete time, it can only take integer values, but it cannot take fractional values. Now here we are going to explain more detail about this continuous time signals. So the continuous time signal, it is denoted by x of t, and you have to note down that the independent variable is the time. The continuous time is denoted by t, and this t can take all positive and negative integer values and all positive and negative fractional values as well, except irrational values. So for example, if we take a continuous time signal x of t, the valid values of this continuous time variable t are t equal to 10, it's an integer, it's valid. T is 1.5, it is a fraction, that is also valid. If you take a negative fraction t equal to minus 10.55, that is also valid. We can even take a very longer fraction with lot of decimal places as given here, and this is also a valid time because we can take all fractional values for the continuous time t. Now what are the values of time that are not valid? If you take irrational values, for example t is equal to square root of 2 or t is equal to pi, these are irrational values, and hence that is not a valid value of continuous time, because time has to be precise. And if we take the time value as a irrational number, for example t is equal to square root of 2, the square root of 2 is 1.41414, it is going on as a indefinite decimal places, therefore the value of the time is not precise, and hence we cannot take these irrational numbers for the continuous time values or any time values in general. So time cannot be irrational, time has to be precise. Now we are going to discuss discrete time signals, which are also called discrete time sequences, and they are represented by x of n. Here n is called the discrete time, and n can take all positive and negative integer values only. The discrete time variable n cannot take the fractional values, and of course it cannot take the irrational values as well. So let us see some examples of the valid discrete time, which is n. Of course we can take n is equal to 10, 10 is an integer. We can take n equal to 0, 0 is also an integer. N is equal to minus 100, that's a valid discrete time, that's also a negative integer. Now let us see what are the values that are not valid for the discrete time n. If you take n equal to 1.5, it is a fraction, therefore this is not valid discrete time, because again if you see the definition, discrete time n cannot take positive negative fractional values. Similarly, if you take n is minus 10.55, again it's a fraction, again n is equal to square root of 2, that is not valid because these are irrational. Now we are going to discuss another classification of the signals, which is deterministic versus random signals. Now, what is a deterministic signal? A deterministic signal is a signal for all the values of the time. The signal values, that is the values of x of t, they are well defined, and these signals, they can be represented by some formulas. For example, x of t is e power minus t. For each and every value of t, we know what is the value of e power minus t. Therefore, the signal is well defined for each and every instant of time t. Now let us take another deterministic signal, which is y of t is sine 2 pi t. Now again, for each and every value of t, this sine 2 pi t is having a distinct value. Therefore, y of t is well defined for all the time instants. Therefore, this y of t, which is sine 2 pi t, is also a deterministic signal. Now we are going to discuss the signal which is a random signal. This random signal is also called stochastic signal, and this is a signal where the value of the signal x of t cannot be predicted or completely defined before or ahead of the time, and it cannot be reproduced by using a particular process or a mathematical function or by using a table. So with respect to this random signal, there is a certain amount of uncertainty about the values of the signal. Therefore, it is called a random signal. Therefore, it is called a stochastic signal, because there is lot of uncertainty about the values of the signal. Now, an example of this random signal is the very basic speech signal. So, if you are talking to your friend, you are hearing his words as a speech signal. You cannot guess what are the words of speech which your friend is going to speak after 5 seconds. So, there is an uncertainty about the values of that speech signal, because those speech signals you cannot know as a completely defined values before those speech words are uttered. Now another example is a seismic signal, which is an earthquake signal, which is also a random occurrence, and this is also a random signal, the seismic signal, which is the signals of measuring the earthquake, the velocity or acceleration or the force which is representing that earthquake. So the random signals or stochastic signals, they are actually related to the natural phenomenon of the speech or the earthquake or generation of some music by some instrument. And all these random signals, they are the part of real life. And again, you have to understand the random signals or stochastic signals, even though there is a certain uncertainty that is associated with that random signal or stochastic signal, they are part of the real world life. Now here we are going to see the pictorial description of the deterministic signal e power minus t. Now since we have given a negative exponential, that is e power minus t, the power is negative, the signal is continuously decreasing, therefore this is a decaying exponential. Now here on the other side we are showing a random signal, the speech signal as the example. It is showing the waveform of the speech signal. And you can see, as the speaker is speaking, there are certain pauses between the waveforms. And you can always observe by your own experience, as you talk, you are going to take some brief pauses in your speech. So here you can note down all these pauses between the words of the speaker. Now we are going to discuss another classification, which is periodic signal versus non-periodic signal. A periodic signal, it satisfies the periodicity property, which is x of t is x of t plus k into t naught, where t naught is called the fundamental time period. So this periodic signal, it keeps repeating itself for every t naught seconds. And we can also define the fundamental frequency f naught as 1 by t naught. And we can also define the angular frequency omega naught, which is directly related to the frequency f naught, as omega naught is equal to 2 pi into f naught. So if you know the fundamental frequency or the frequency f naught, we can also calculate the angular frequency. If you know the angular frequency, we can calculate the frequency, and both are like twins or like brothers. If you know the frequency, you can calculate angular frequency by simply multiplying with 2 pi. Now, what is a non-periodic signal? The non-periodic signal is also called a periodic signal. It is not periodic. Therefore, it does not have the repetition. Therefore, the definition of the non-periodic signal is simply x of t is not equal to x of t plus k into t naught. So there is no repetition. Since the repetition is not there, we are simply having inequality. Now, we are showing the pictorial description of a periodic signal. Here we see a triangular signal is getting repeated at different intervals of time. Now here we can see another shape of the signal, which is a periodic signal, and this is now a discrete time periodic signal. Now on the right side you can see a non-periodic signal. Here the signal is 0 on all negative time and it is 1 on positive time. This signal is non-periodic because the basic shape of this signal is not repeating. It might be continuously 0 on the negative side and it might be continuously 1 on positive side, but a single piece or structure of the waveform is not repeating. Therefore, this is a non-periodic signal. Now we are going to discuss another classification, which is real versus complex signals. This is a very simple classification based on the values which the signal takes. So a real signal, it takes the values from the set of real numbers. Therefore, x of t, it belongs to the set of the real numbers. So each and every value of the signal x of t is belonging to the set of real numbers. Now, a complex signal, it will take the values from the set of complex numbers. For example, 2 plus 3j or 5 plus 6j, where j is the complex number, which is the square root of -1. So the complex signal is actually taking the values which are from the set of complex numbers. Now, these complex signals, they can be represented by combining two real signals. If you take a simple example, I can write a complex number C as a plus j into b. So a is a real number, so we can get a real signal, and the other factor is what? J into b. Again, that b is also a real number. From there we can get another sequence of real numbers which will represent a real signal. Therefore, I can write this complex signal as the sum of two real signals. So the complex signal is actually a mathematical representation of different set of signals that are somewhat related to each other. Now we are going to discuss a very important classification, that is causal signal versus non-causal signals. Now this causal signal is very important for a practical system that can be realized in real world. And these causal signals, they are the real world signals that are being produced by the physical devices or the equipments in the lab or in industries. Now we can define the causal signal as the causal signal is a signal whose values on the negative time are 0. So if the signal values on the negative time, that is t less than 0, all those signal values are 0, the system is the signal is called a causal signal. So what is a causal signal means, for all the negative time values, that is t less than 0, the signal values must be 0. Now a signal that doesn't satisfy this property, that the signal values are 0 for negative time, that is t less than 0, that is called a non-causal signal. Now here we are discussing another classification, even versus odd signals. Now a signal is supposed to be called even signal if it satisfies the property x of t is equal to x of minus t, where x of minus t is the time reverse signal. So if the time reversed signal x of minus t is equal to itself, that is x of t, the signal is called even signal. Now we can see from this equation that the even signals, they will be symmetric. So if you see the even signals, for example here, the signal x of n, the shape of the signal on the positive time and the negative time is same. So the even signal is also called a symmetric signal. Now even this continuous time signal, this is also even signal because it is symmetric about the y-axis. So all the even signals, they will be symmetric about the y-axis. So by interchanging the negative time and positive time, we are going to get the same signal back. Hence the even signals, they are symmetric about the y-axis. Now what is an odd signal? An odd signal is anti-symmetric. So if I take x of minus t, that will be equal to minus of x of t. So if we take the time reversed signal x of minus t, it will be minus of the original signal, that is minus of x of t. So it is anti-symmetric. So if you see here, this odd signal, we are having the values of the signal on positive time as positive, but on negative time as negative. So this is a anti-symmetric signal. Therefore, this is a odd signal. Now another important concept is any signal can be represented as a combination of the even part and odd part. So any general signal x of t can be written as the even part xe of t plus the odd part, which is xo of t. Now we are going to discuss another classification, which is energy signal versus power signal. So before we do the classification, we have to define what is energy, what is power. So the signal energy of a signal is simply the area under the curve of that signal. We can write the signal energy, which is represented or denoted by E of x, as limit t tends to infinity integral minus t to t mod of x of t whole square dt. So we are taking the square of the magnitude of the signal and we are integrating over its entire duration. So that is the energy of the signal. Now what is the power of the signal, the average power? We know from physics that power is energy per unit time. So we have to divide the energy by the total time duration, which is going from minus t to t. So the total duration will be 2t. So if you know the energy formula, we can simply get the power formula by dividing by the time. So the average power p will be limit t tends to infinity, the same thing as here, and the integral is also same, integral minus t to t mod of x of t whole square dt, but we have to divide by the time, which is 1 by 2t. So the average power p of x is limit t tends to infinity 1 by 2t integral x of t mod whole square dt. Now what is energy signal? The energy signal is a signal that has finite energy, and that signal will satisfy this condition. E of x should be less than infinity, and at the same time E of x should be greater than 0. So the energy signal is a signal that satisfies the condition that E of x is less than infinity, and at the same time E of x is greater than 0. So E of x must not be 0. Now for this type of energy signal, the power of the signal will be 0, P of x equal to 0. So we can always tell the energy signal has 0 power. Okay. Now we come to the power signal classification. A power signal is a signal that satisfies this condition, that here power P of x should be finite and the power should also be non-zero. So therefore P of x should be greater than 0 and P of x should be less than infinity. Now for any of such power signals, the energy of the signal E of x will be infinity. Okay, so for a power signal, energy E of x will be infinity. Now I want to thank all the audience for your patient hearing. Thank you.